So here's another thing we could think about with modular arithmetic. We could go a little more general, a little more abstract. Number 2 here is looking to see if we can prove a very familiar property. When you square the sum of two quantities, square a binomial, do you get the standard perfect square trinomial formula, a squared plus 2ab plus b squared? Well, we're going to see that that is true because it follows just from the fundamental properties that z mod n, modular arithmetic, shares in common with ordinary real number arithmetic, and that's the properties of being a ring, which is the list of properties in our book that's on page 318. Okay, so what's the definition of a plus b squared? It's just a plus b times itself. Now, I'm not going to pronounce the bars everywhere, but I'm trying to write it really carefully now with those bars to emphasize that these, you want to think of them as numbers that live in this new number system. Okay? And we're just going to use the properties of that number system. It's really nice. We are not actually going to have to refer back all the way to how z mod n relates to ordinary integers. Okay. So now I can use the distributive law, or one of the distributive laws. Okay. I could then take that whole thing, a plus b times a alone, and then also I'll just copy and paste and then just modify a plus b times b alone. So I'm distributing out this quantity times these two things separated. This is exactly, literally symbol for symbol, well, except without the bars, I guess, how you would prove this fact is true for ordinary real numbers. So you get a times a plus b times a plus a times b, and then plus b, maybe I should copy and paste the b, huh? B times b. And that's by definition, that's the a bar squared. And one last rule, that addition is commutative. We've seen that in the tables. We know it's true because it's just true for integers as well. And so we get two copies of a, b. And then, of course, b times b is just b squared. B squared. And we're done. Okay. So the point is that there's going to be a lot of familiar stuff in algebra that's going to hold just as well in z mod n, as long as it only comes from things like commutativity, associativity, distributivity of addition and multiplication. But here's an interesting twist. There's something, this is true in any z mod n, including z mod 2, but I claim that there's something that's rather special that happens additionally in z mod 2. Okay, so I'm going to write this down again. You might want to think, what is special? Pause the video and see what's special about this when you're looking at z mod 2 specifically. Well, let's look at the middle term. You're taking something and you're multiplying it by 2. Well, 2 in z mod 2 is the same as 0. So it just dies. Another thing, if you want to take it back to ordinary integers, we can think, okay, z mod 2 means we're doing these calculations with ordinary integers, but we always take the remainder mod 2. Or in other words, any even number is considered a 0. Well, that's certainly an even number if you translated it back to ordinary integers. So in fact, what you get is what a lot of people will give under stress, or if they're just kind of new at algebra, a lot of people will say, oh, the square of a sum, maybe that's just the sum of the squares. That's just not true anywhere but in z mod 2. So let me be careful. I'm not saying, okay, now you can go back to your calculus class and use that. That is a true fact in z mod 2, but really pretty much nowhere else. Okay, so that's kind of cool. Familiar rule, but then an unfamiliar twist.